To that end, I'd like to highlight today on the reciprocal control of the intercellular transfer of one particular microRNA we want to do, and an anti-microRNA signals that regulate the proliferation and growth of the hepatic cells. So we all know about the central dogma of genetic molecular biology, where the DNA is transcribed to RNA and then is translated to protein. But that gets modified with the introduction of the non-coding RNA called microRNA, which can regulate different steps of this process, and we primarily do so getting transcribed from the genome from a different locus and bind to the target RNA with an imperfect complementarity, and by binding it regulate the expression of proteins of the target genes and induce the translational separation and also the degradation. So these are the microRNA that are primarily transcribed as a pri-microRNA transcribed that are processed inside the nucleus to the pre-microRNA that are exported and then matured into the cytoplasm by the dicer TRBB protein complex and generated 22 nucleotide double-stranded form. One of the strands encoding the microRNA get incorporated into the Argonaut proteins, and that Argonaut microRNA complex find their target genes where they bind with the perfect and imperfect complementarity and induce translational repression and deregulation of the target genes. So there are thousands of microRNA operators in humans. There are 22 nucleotide long regulatory RNA. Almost 50% of the human genes are under microRNA regulations. They regulate different stages of development, differentiation, apoptosis, and so on, and their expression pattern is dysregulated in human diseases. They also control different developmental and species-specific expression patterns, and they show specific microRNA expressed in brain, liver, and muscle. So my lab is working on the modulation of microRNA activity. As you can see, the microRNA regulate almost 50% of genes, so therefore the regulation of microRNA is very important to control the gene expression. To that end, we are working on different modules. One of them is the alteration of microRNA function during the Leishmania infection process in the macrophage, and we want to see how microRNA can affect the process. On the other hand, we are also working heavily on the regulation of intra and intercellular microRNA transport, and of course we have other interest in the microRNA regulation process. So to start with, I'd like to mention that what are the role of microRNA in modulation of host culture interaction, and use Leishmania macrophage as an interacting working model. We find that indeed Leishmania secrete a protein called GB63 that are targeted to the hepatic cells, and where it downregulates the enzyme dicer to inhibit the processing of pre-microRNA to the mature one, and in that way reduce the production of microRNA 1, 2 to lower the serum cholesterol, because B12 is known to regulate the serum cholesterol level, and therefore it affects the process of cholesterol production. And we published the paper earlier in the Cell Host Microbes Journal, the Cell Press Journal, where Leishmania don't want to target dicer 1 to downregulate microRNA 1, 2 to lower serum cholesterol and facilitate murine liver infections. And that potentiates the role of microRNA as a therapeutic molecule against the visceral Leishmaniasis or collagen. So the other aspect, we are heavily working on the regulation of intra and intercellular microRNA transfer. Why is important? MicroRNA are not static, they are transferred in one cell, but they can be transferred from this cell to the neighboring cells as a part of small vesicles called exosome, and they can be part of, can be absorbed with the HDL or other RNA-binding protein before they can transfer to the neighboring cells. And in that way, the extracellular transfer of microRNA via extracellular vesicles is another way of controlling the cellular level of microRNA and its activity. So regulation of microRNA export is an effective way to control the gene expression process. And to understand that, I'd like to introduce the exosome here. Exosomes are 30 to 90 nanometer vesicles that are secreted by a wide range of cells and contain both proteins and RNA. Are derived from multivesicular endosomes that fuse with the plasma membrane and sets into the extracellular space. They help in cell-to-cell communication by transporting various proteins, messenger RNA, and of course microRNA. And they can be separated easily by centrifugation from the cultural superconductor of cells, and they are present in the body fluid like urine, plasma, and they can be studied in this body fluid as well. So regulation of exosomal export of microRNA is an interesting field and emerging field, and we have started working on this field. where we're looking into this microRNA 1 to 2, a liver-specific microRNA that represents 70% of the liver microRNA population, and has been characterized for its multiple roles in liver physiology, metabolism, and in modulation of hepatitis C virus replication. And importantly, loss of or downregulation of this microRNA has been associated with the human and rodent hepatocellular carcinoma development and progression. And we want to knock out mice develop spontaneous hepatocellular carcinoma with age. So this is an anti-proliferative microRNA. The question will start. So when you have a lump of cells, maybe one cell starts losing that particular microRNA that controls the growth of that cell. So the neighboring cells try to compensate that loss, probably by secreting some of the microRNA via exosome that can be delivered to the target cells and compensate that loss. But when there is a problem of this kind of transfer, then only that population of cells that have lacked the microRNA start proliferating more and becoming metastatic, and the tumors are formed. So we like to study the intracellular transfer of the tumor suppressor microRNA in the liver cancer cells. So we use two kinds of cells. One is the HG2, which doesn't have the microRNA 1 to 2, and another is the HH7 cell, which does have the microRNA. And they are tagged with two different fluorochromes, in case of GFP and BS red. They can be seated together and can be, after co-culturing, can be separated based on the fluorescent sorting of the GFP and BS red population of cells. So this is our in vitro model to study the transfer of microRNA from this HH7 cell to the HG2 cells and so on. So we have found the reporter that can tell us about the microRNA get transferred or not. We find that microRNA activity in the recipient HG2 cell gets increased when they are co-cultured in presence of the microRNA donor HH7 cells. And this activity increase is manifested also with the increase in the microRNA content in the target cells, but that suggests that physically the microRNA get transferred from these cells to that cell to replace the microRNA target genes in case it is reported, but also for the endogenous target as well. So, co-cultured and sorted HG2 cells show the decreased level of microRNA 1 to target mRNA, which is consistent with the increased level of intracellular microRNA 1 to 2. So, how it can be transferred? As I mentioned, exosome is one of the way of transferring microRNA.